Section: Introduction. In this section, we discuss generative models for continuous domains, which have led to various applications in images, videos, and audio. However, we face ongoing challenges in achieving high-quality outputs, efficient inference, and stable training, what we refer to as a trilemma that drives our research. One prominent technique, diffusion models, often requires many steps for quality results. Meanwhile, methods like diffusion distillation and consistency models can lead to training issues if not carefully managed. To tackle this trilemma, we present Inductive Moment Matching, IMM, a stable training approach that allows us to learn generative models from scratch for both single and multi-step inference. IMM focuses on the time-dependent distributions of stochastic interpolants, which are continuous processes linking two probability distributions, data at the start and a prior at the end. By learning how to map any distribution at a given time to another earlier time, we can effectively support one or multiple steps of generation. We can train IMM efficiently using mathematical induction. For any time between 2 points, we create two distributions by applying a one-step IMM from samples at those points and minimize their differences to ensure independence from the starting times. This method guarantees that we converge to the actual data distribution. To enhance training stability, we base IMM on specific stochastic interpolants and use stable divergence estimators for optimization. Interestingly, we demonstrate that consistency models are a specific case of IMM, which helps explain their training instability. Our results show that on the ImageNet dataset, IMM outperforms diffusion models, achieving a low Frechet inception distance, FID, with just 8 inference steps using standard transformer architectures. Similarly, on CIFAR-10, IMM reaches state-of-the-art performance with a low FID using a 2-step generation process from a model trained from scratch. Next, we cover the basics of diffusion, flow matching, and interpolants. For a given data distribution, variance-preserving diffusion models and flow matching create time-augmented variables as interpolations between data and a prior. We define these variables in a way that allows us to train models by matching the conditional velocity, which a neural network approximates. We can generate samples using a probability flow ordinary differential equation starting from the prior distribution. Stochastic interpolants unify diffusion models and flow matching by constructing a conditional interpolation between any data and prior, with specific constraints. We can learn a deterministic sampler by matching the conditional interpolant velocity. Sampling follows a similar process as before, starting from the prior. When certain conditions are met, stochastic interpolants simplify to the velocity prediction diffusion model. Section Summary. In this section, we introduce Inductive Moment Matching, IMM, a novel training procedure for generative models that addresses the challenges of high-fidelity outputs and stable training by learning from time-dependent marginal distributions. We demonstrate that IMM outperforms existing diffusion models on benchmark datasets, achieving state-of-the-art results with significantly fewer inference steps. Section: Maximum Mean Discrepancy. In this section, we discuss maximum mean discrepancy, MMD, which measures the difference between two distributions, P, X, and Q, Y, where X and Y are in a d-dimensional space. MMD is defined using an integral probability metric in a reproducing kernel Hilbert space, RKHS, with a positive definite kernel. For instance, using the radial basis function, RBF, kernel allows us to consider an infinite-dimensional feature space that includes all moments of the distributions. Next, we introduce Inductive Moment Matching, IMM, a method that efficiently trains a model in one stage. We assume a time-augmented interpolation between the data distribution at time 0 and the prior distribution at time 1. Our goal is to learn a one-step model that can transform the distribution at any time t to an earlier time s. This model allows us to sample directly from time 1 to time 0 and to perform recursive sampling from any time t to any earlier time s, enabling us to learn from our own samples through bootstrapping. We then focus on model construction using interpolants. Given data x sampled from Q, x, and prior epsilon sampled from p, epsilon, we define a time-augmented interpolation x_t that follows a specific distribution. This leads us to learn a model distribution defined by a one-step sampler that transforms q_t, x_t, into q_s, x_s, for any s less than or equal to t. We utilize a special class of interpolants that maintain the marginal distribution while interpolating between x and x_t. We call these marginal preserving interpolants. We formally define x_s as a generalized interpolant between x and x_t, ensuring that it meets certain constraints. When t equals 1, it simplifies to regular stochastic interpolants. We also define our noisy model distribution at any time s, which is marginal preserving and parameterized as a one-step sampler. To generate a clean sample x from x_t in 2 steps, we first sample from our model distribution and then from the interpolated distribution. If the marginal of the intermediate sample matches the desired distribution, we can obtain our final sample. Our aim is to minimize the divergence between our model and the target distribution using a specific objective. We note that while we can easily draw samples from our model, we can also learn it by minimizing the divergence with respect to a time distribution and a sample-based metric like MMD or GAN. If the interpolant is marginal preserving, the minimum loss is 0. However, matching the distributions does not guarantee uniqueness in the minimizer, although under certain conditions, a deterministic minimizer can exist. Section Summary. In this section, we introduce maximum mean discrepancy, MMD, as a metric for comparing distributions in reproducing kernel Hilbert space and present inductive moment matching, IMM, a method for efficiently training a one-step sampler that interpolates between data and prior distributions. We also define marginal preserving interpolants that maintain the marginal distribution during the interpolation process, enabling effective multi-step sampling and model learning through minimizing divergence metrics like MMD. Section: Learning via inductive bootstrapping. In this section, we discuss learning through inductive bootstrapping. We recognize that the straightforward objective we mentioned is challenging to optimize because when the time point t is far from s, the input distribution can differ significantly from the target distribution. However, our method ensures that the model meets the boundary condition, meaning that when t is close to s, the model's output closely matches the target distribution. Additionally, our approach guarantees that the model's output for t is similar to that for any nearby r, allowing us to create an inductive learning algorithm using samples from the model at r. To analyze this better, we define a sequence for the model parameters and a function that helps us learn to match the output at r. We aim to optimize the model parameters using a specific objective that incorporates a weighting function. We choose the maximum mean discrepancy, MMD, as our objective because it provides stable optimization and effectively learns the correct data distribution. We also present algorithmic considerations, noting that while our theoretical framework is solid, selecting a suitable marginal preserving interpolant can be tricky. We provide a condition for ensuring marginal preservation, which states that the distribution of S remains consistent whether we sample it directly or through an intermediate sample. We introduce the denoising diffusion implicit models, DDIM, as a fast sampling method for diffusion models. We show that DDIM can be used as a self-consistent interpolant, allowing us to define a deterministic model for generating samples. To eliminate randomness, we utilize the DDIM interpolant and a deterministic model, ensuring that we can generate samples from the model effectively. We also discuss reusing samples to reduce variance, which helps maintain the target distribution. We set the optimization step number and clarify that we can simplify our notation by treating the previous parameter as a stop gradient parameter. Our training objective is derived from the MMD definition, and we explain how to empirically estimate this objective using particle samples. In practice, we organize our model outputs into groups to approximate the distributions efficiently, ensuring that the number of model passes remains constant. We visualize a simplified version of our training algorithm and provide a complete training algorithm in the appendix. Section Summary. In this section, we present an inductive learning algorithm that optimizes the model parameters to match target distributions by leveraging a marginal preserving interpolant, ensuring that the model remains consistent and stable during training. We also discuss practical considerations for implementing this algorithm, including the use of deterministic models and variance reduction techniques to enhance sample generation from the target distribution. Section: Other implementation choices. In this section, we explore various implementation choices related to flow trajectories and network configurations. We focus on two common flow trajectories: cosine, where the first component is the cosine of half pi times time, and the second component is the sine of half pi times time, and OTFM, where the first component decreases linearly from 1 to 0, and the second component increases linearly from 0 to 1. For our network, we define a function that combines a skip connection with a neural network output, following the EDM approach. We set a specific value for one of the coefficients to ensure proper scaling. We also outline several valid choices for other coefficients, including options for identity, simple EDM, and Euler FM, which is specific to the OTFM schedule. We find that our noise conditioning works well when we use a constant multiplied by time. We recommend a larger constant to help distinguish between close values. For the mapping function, we determine that a constant decrement works effectively, and we specify how to choose this decrement. We utilize time-dependent Laplace kernels for better gradient signals compared to RBF kernels. Our weighting and distribution follow the VDM approach, defining uniform distributions for time and a sigmoid function for weighting. For sampling, we describe push-forward sampling, where we can obtain samples by applying our function iteratively, starting from a noise distribution. This process is akin to a few-step sampler using the learned network. We also introduce a restart sampling method that adds randomness by reintroducing noise before sampling again. Lastly, we discuss classifier-free guidance, where we adjust the model output based on a data label pair during inference. We define our guided model similarly to the original, simplifying notation by omitting certain components. We justify our choices in the appendix and provide details on the sampling algorithms there as well. Section Summary. In this section, we explore various implementation choices for flow trajectories and network configurations, detailing specific parametrizations and coefficients used in our model. We also discuss sampling methods, including push-forward and restart sampling, as well as classifier-free guidance, emphasizing their roles in enhancing model performance and flexibility. Section: Connection with prior works. In this section, we connect our work with various prior studies, with a detailed analysis available in the appendix. We discuss consistency models, CMs, which utilize a network that produces clean data from noisy input. These models require a specific consistency condition, where the output for a noisy input at a later time must match the output for a less noisy input obtained through an ODE solver. For discrete time CMs, we need the output at the initial time to equal the initial input, and we train the model using a loss function that measures the difference between the outputs of two networks, typically using a distance metric like L2 or LPIPS. We demonstrate that the CM objective using L2 distance serves as a single particle estimate of a more complex objective involving an energy kernel. However, this single particle approach overlooks certain forces, which can lead to biases and instability in training. To address this, improved CMs suggest using a pseudo-Huber loss, which we justify in another lemma. This loss matches all moments of the distributions, enhancing performance. We also explore other valid kernel choices and extend the IMM loss to a continuous limit, which we plan to investigate further in future work. Next, we discuss diffusion GAN and adversarial consistency distillation, where diffusion GAN defines a generative distribution that incorporates randomness to improve sampling. Both methods utilize a GAN objective, which is similar to MMD, allowing us to avoid explicit adversarial training. The Generative Moment Matching Network, GMMN, applies MMD to train a generator to match the data distribution, simplifying to a basic GMMN objective under certain conditions. We also review related works, including diffusion models and flow matching, which have been effectively used for various tasks. Stochastic interpolants build on these concepts by defining a stochastic path for distribution transfer. Recent methods aim to improve the sampling efficiency of diffusion models, but they often require careful tuning and can lead to issues like mode collapse. In contrast, our approach matches all moments using MMD and can be trained from scratch without needing multiple networks or special training practices. Overall, our method achieves stable training and strong performance without the complexities seen in other models. Section Summary. In this section, we connect our work to prior research on consistency models and generative frameworks, highlighting how our method improves training stability and performance by implicitly matching all moments of the data distribution using MMD, unlike existing models that often require complex training practices. We also discuss the limitations of previous approaches, such as the need for specialized components and the challenges of adversarial training, emphasizing the advantages of our single loss framework. Section: Experiments. In this section, we evaluate the empirical performance of IMM, focusing on aspects such as training stability, sampling choices, scaling behavior, and our practical decisions. For image generation, we present FID results for unconditional CIFAR-10 and class-conditional ImageNet 256 by 256. We categorize baselines into diffusion and flow models, distillation models, and few-step models from scratch. IMM falls into the last category, achieving a state-of-the-art performance of 1.98 using a push-forward sampler. For ImageNet 256 by 256, we utilize the DIT architecture due to its scalability and compare it with various models, including GANs and diffusion models. We notice that FID decreases with more steps, with IMM reaching 1.99 FID using 8 steps, which outperforms DIT and CIT with the same architecture, except for a minor adjustment in time injection. Impressively, we achieve better 8-step FID than the 10-step VAR of similar size, nearing the performance of its larger variant. Unlike VAR, IMM allows for a flexible number of inference steps, enhancing scalability during inference. Additionally, IMM matches MAR's performance while being 10 times faster, showcasing its efficient scaling capability. We also exceed the best performance of shortcut models with just 8 steps, and we provide further inference details in the relevant sections. Regarding training stability, we demonstrate that IMM remains stable and performs well across various parameter choices. We compare positional and Fourier embeddings, noting that while Fourier embeddings can lead to instability at a scale of 16, IMM does not encounter this issue. We use the NCSN++ architecture for Fourier embeddings and DDPM++ for positional embeddings, both of which converge reliably. The number of particles, m, used for estimating MMD is crucial for our empirical success. A larger m improves accuracy, but simply increasing it can slow convergence due to our fixed batch size. We find that using too few particles, like m equals 2, leads to instability, especially with larger architectures. We identify an optimal range for m, where a few particles enhance stability, but increasing m beyond a certain point hinders convergence. Specifically, in ImageNet 256 by 256, training fails with m equals 1 and m equals 2, while m equals 4 yields the best FID under the same computational budget. We also explore noise embedding, observing that increasing the distinguishability of nearby distributions improves performance. Our framework shows consistent convergence across different settings. In terms of sampling, we examine various settings for optimal performance. For CIFAR-10, we use 2 steps with a specific intermediate time that works well. For ImageNet 256 by 256, we explore both uniform decrement in time and an EDM schedule. Our findings indicate that push-forward samplers with a uniform schedule perform best for ImageNet 256 by 256, which we adopt as our default for multi-step generation. We acknowledge that combining push-forward with restart samplers could yield even better results, which we plan to investigate in future work. Section Summary. In this section, we evaluate the empirical performance, training stability, and sampling strategies of our model, IMM, demonstrating its state-of-the-art FID scores on CIFAR-10 and ImageNet 256x256. We find that IMM achieves efficient inference with flexible step counts, maintains stability across various parameter choices, and identifies optimal particle numbers for training, ultimately surpassing other models while ensuring faster convergence. Section: Scaling Behavior. In this section, we examine the scaling behavior of our models. Similar to diffusion models, our models scale with the amount of compute used during training and inference, as well as the model size on ImageNet with a resolution of 256 by 256. We present a plot showing the relationship between the Frechet inception distance, FID, and the compute in GFLOPs, revealing a strong correlation between the compute used and the model's performance. We also visualize sample quality as we increase model size, specifically, from small to large transformers, and as we increase the number of inference steps. We observe that larger models and more inference steps lead to better sample quality, as they can capture more complex data distributions. This also explains why using more compute can sometimes produce different visual outputs from the same initial noise. For our ablation studies, we utilize the DDPM++ architecture for CIFAR-10 and DIT-B for ImageNet. We default to using two-step samplers for FID comparisons and refer readers to the appendix for additional studies on flow schedules and network parametrizations. We explore various combinations of network parametrizations and flow schedules, including simple EDM with cosine, simple EDM with OTFM, Euler FM with OTFM, and identity with both cosine and OTFM. We find that identity parameterization consistently performs worse than the others, which shows similar results across datasets. On the smaller CIFAR-10 dataset, simple EDM with OTFM performs best, while on the larger ImageNet dataset, Euler FM is superior, suggesting that the OTFM schedule and Euler parameterization may be more scalable. Regarding the mapping function, we test several approaches, including constant decrements in various parameters. For a fair comparison, we ensure that the minimum value of a specific function is approximately 0.001 and use the same network parameterization. Our results indicate that the first approach consistently outperforms the others. We also investigate the mapping gap using a specific value and find that performance remains stable for certain values but becomes unstable at higher ones, indicating a limit for stable optimization based on particle numbers. Finally, we analyze the weighting factors in three groups: the VDMELBO factors, the weighting of alpha, and the weighting of a specific function. We determine that using alpha in conjunction with ELBO weighting is essential, as it aligns the V-pred network with the epsilon-pred parameterization. Additionally, upweighting middle time steps enhances performance, a practice known to benefit FM training. We explore the exponent in the appendix and find that different values emphasize different aspects of optimization, with one value achieving higher quality in multi-step generation than another.